Alright, today I'm going to launch right into the recap and start with a review of the electrochemical cell, a very important concept both for general electrochemistry principles and for analytical, which we're building up to. I'm going to quickly go through the process of building up this cell the way that we did before. This time it'll be a little bit more animated since in principle you've already drawn everything that I'm going through. So first we started with our two electrodes, zinc and copper, in separate beakers. And then we filled the beakers with 1 molar solution that contains the cation form of the respective electrode on each side, and some charge balancing sulfate ions that presumably won't react, as that could cause complications. They're just there to balance charge. The significance of saying that these solutions are at 1 molar is that we can say that these solutions are at standard state, which is important for later. Now we call each of these sides a half cell, because they come together to build the full electrochemical cell. But we need more than just solutions and electrodes. We need some type of connection between the two, and that connection would be in the form of wires. And these wires are connected to some type of electrical device. In this case, we're going to use something called a voltmeter, which I'll get into later, but it could be like a light bulb, just something that we're trying to power via the electric current as redox reactions release electrons that go from one side to the other. And the first major notes that we wrote underneath our drawing were how to figure out which half cell generates the electrons. In other words, which side is going to involve oxidation and produce electrons, which will travel to the other side where reduction will occur. And we figure that out by evaluating the potential reduction half reactions that can occur in each solution. On the right side, the possible reduction reaction is that electrons would go into the copper 2 plus solution and reduce Cu2 plus to form more copper. Chemically, we would represent the reaction like so. On the other side, a similar reduction reaction could potentially occur, where zinc 2 plus gains 2 electrons and forms more zinc solid. So the question is, which of these actually happens and which one will be forced to go the other way? Because they can't both be gaining electrons. Someone's got to lose the electrons so the other one can take them. And so we evaluate their reduction potentials. These are the voltages associated with each half reaction written from the reduction point of view. And we recall that a positive voltage is favorable energetically. We also quickly recall that E naught means this is the voltage at standard state, so these only apply when our solutions are at 1 molar aqueous species. We'll get into voltages when they're not at standard state later. And so in this case, it's very obvious which one's more positive than the other, given that the zinc reaction is negative, which implies it's unfavorable, especially relative to that positive 0.339 volts. Sometimes it's not as obvious. Sometimes both possible half reactions are going to be positive or negative. All that matters is which one's more positive. That is ultimately going to be the one that wins the day for reduction, and the other one will have no choice but to go in reverse and be oxidized. But that flips the sign when we look at it from the reverse point of view. So the overall reaction that occurs between both sides is this reaction here, where zinc is oxidized to Zn2+, and those 2 electrons that were lost are ultimately gained by copper 2+, forming more copper solid. Thus, we say that copper is the cathode and zinc is the anode. Copper is where reduction will occur, anode is where oxidation will occur. And so we can visualize that process as electrons moving from the zinc over to the copper side. And as they're moving through this wire and passing through this device, we can harness that energy associated with the electron transfer, the same way a water wheel harnesses the energy of water as it passes from a higher point to a lower point. We don't consume the water, we just use it along the way. The device does not consume the electrons, they ultimately make it here. We just utilize some of this energy associated with the reaction, because that's what volt really means. It's how many joules of energy can we get per coulomb of charge. And those electrons are carrying charge. We learned how to relate electrons to coulombs of charge in the previous lecture. Now, as this redox process occurs, we run into a problem. As oxidation occurs on the anode side, we generate zinc 2+. As reduction occurs on the cathode side, we lose copper 2+. Problem is, the negative sulfate ions are not changing concentration at all since they have nothing to do with this reaction. And so both sides become uncharged balanced. 2 positive, 2 negative. Or not positive enough. And so the way we combat this issue is with a salt bridge. A salt bridge's function is to transport ions in or out of these solutions to maintain charge balance. So on the left side, if we create this excess positive 2 charge, we'll balance that by bringing in 2 negative chloride ions from the salt bridge. And ideally, these chloride ions will just be spectator ions in solution and not cause any side reactions that could affect our electrochemical cell. That's the ideal. They just balance that excess charge. On the right side, to make up for the fact that we just lost the Cu2+ ion, we can funnel in 2 positive potassium ions. Same logic. Another way the salt bridge could potentially function is instead of putting new ions into solution, it could take excess charge out. So instead, maybe the salt bridge would take zinc 2+ into itself, while also taking sulfate ions from the other side, which would also, in principle, reestablish charge balance in each solution. But I'm only animating the more common use of a salt bridge. So that gets us to where we left off before. The only thing left to address is what is this voltmeter that we drew? And before we talk about it, let's just add a tiny detail to it. Put a negative sign on the left side and a positive sign on the right. And then note that the picture you should be seeing without all the animations is this. It's a lot of information, and that's why it's nice to be able to just animate that slide from before and see how we built it all up. Although eventually you should be able to just look at something like this and immediately be able to interpret everything you're seeing. Anywho, let's talk about that voltmeter. First of all, what is a voltmeter? Some of you very well may have seen one of these in real life, but for those of you who haven't, one of its major functions is to measure the voltage that exists between two electrodes. Conventionally, the red wire is labeled positive and the black wire is labeled negative. And then we attach these wires to the electrodes in, say, a battery, which is an electrochemical cell, and we hook up that positive wire to the positive electrode and the negative wire to the negative electrode. At least that's how we would ideally hook things up. But if we do that, this device will then measure the overall voltage that exists between the two electrodes. So let's make some notes about this. Adding to what we've already written, we'll call this note number 4, voltmeter. Connects wires from the positive and negative terminals to each electrode. Connects wires from positive, which we'll just write a plus symbol and then a circle, and negative, same deal, terminals to each electrode. Terminals to each electrode. By convention, we put the positive terminal on the right side of our drawings, and the negative terminal is the left side. And when I say terminal, I don't mean the positive and negative electrodes like copper and zinc in our example. I mean the wires that are attached to the voltmeter. So those plus and minus signs that you drew next to the voltmeter. That's what I'm referring to. Or the red and black wires in that voltmeter image. Ideally, the positive terminal is connected to the positive electrode. Positive terminal is connected to the positive electrode. To positive electrode. In other words, the electrode that had the more positive reduction potential, i.e. the cathode. Conversely, the negative terminal is connected to the negative electrode, i.e. the anode. Let's be clear, it's not necessarily a negative voltage associated with that electrode, it's just relatively negative compared to the cathode. So let's add that note in, relatively negative E naught. Relatively negative E naught. For example, and I don't recommend you actually write this, but if the cathode had a standard state reduction potential of 3 volts and the anode was 2 volts, well, they're both positive, but this would be relatively negative compared to that 3 volts. We would say it's minus 1 volt compared to the actual cathode. So that's what I mean. If we hook it up in this manner, then the voltage that the voltmeter reads should equal the voltage of the reaction that we calculated earlier. So let's write this note. In which case, in other words, if we actually have that proper hookup that we already wrote about, we will get the voltage of the reaction equaling the difference between the voltage of the positive terminal minus the voltage of the negative terminal. So let's just make that clear. These signs refer to terminals. Refer to terminals. Both from the reduction point of view. Red POV. And this is what the voltmeter is actually reading. What we'll call E volts. And the book doesn't use this kind of terminology, but I will to make it more clear. The voltmeter is only measuring the difference between the reduction potential of whatever electrode is hooked up to the positive wire and the reduction potential of whatever is hooked up to the negative wire. In our example, the positive wire is hooked up to copper, and the negative wire is hooked up to zinc. And we already solved for the reaction voltage. It was 1.101 volts. And we can refer to the previous slides or your notes and see that the reduction potential of the copper, which is hooked up to the positive wire, was 0.339, and the reduction potential before any flippage occurred of the negative wire's electrode was negative 0.762, which when I subtract from positive 0.339 does in fact give me 1.101 volts. So the voltmeter is going to read that number, which is in complete agreement with the number we calculated earlier. But nothing stops us from hooking everything up backwards and putting the positive wire onto the negative anode. And if we were to hook it up backwards, the voltage reading would actually be flipped. So let's make a note and see what I mean by that. If backwards, in other words, if the positive terminal is hooked up to the anode, the negative electrode, and nothing physically stops us from doing that, and I'll show you what I mean in a moment. But if we hook things up backwards, then the voltage of the spontaneous reaction, which is what we calculated back in note 1, so reaction perspective, will actually be the opposite sign of what the voltmeter winds up calculating, because the voltmeter is just going to take the reduction potential of whatever the positive wire is hooked up to. In this case, we're saying the negative voltage, the anode, minus the reduction potential of whatever the negative wire is hooked up to. And so just imagine I started with the negative 0.762 and then subtracted the positive 0.339. I'd still get 1.101, but it would be negative. So the sign would be in reverse of what the actual reactions voltage is. So I will stress that this is what the voltmeter's perspective is. Now I will say that this whole reaction voltage versus voltmeter reading backwards versus ideal hookup, these concepts can be rather confusing for students at first. And then it eventually just clicks and it's very easy. But until it clicks, it's rather strange. And so I'll definitely bring this up again and try to hammer it out using homework problems as well. For now, I'll just say that when I talk about a backwards hookup being possible, it's kind of like just plugging a battery in reverse into a device. We see the device has a positive and a negative terminal, and the battery itself has a positive and negative electrode. And of course these two should line up, but nothing physically stops me from going backwards. It's just the device won't work, but I can do it. But again, not very useful. A voltmeter would still work, it would just read a negative voltage as opposed to the positive voltage that's actually associated with the spontaneous reactions that should occur in a battery, which are what actually allow our devices to work. Now in standard EChem, there's not much reason to hook things up backwards. But in AChem, that negative voltage reading is just as important as the positive voltage reading. But we'll get there later.